One of the first things you're going to do to determine the identity of a mineral is to figure out its hardness. Hardness is pretty much what it sounds like. Hardness is defined as the resistance to being scratched. So, for example, you have a piece of quartz and you have a piece of glass. Which is harder? All you have to do is try to scratch the glass with the quartz. And you know something? You can. Which means that quartz is harder than glass. There's an entire scale of common minerals called the Mohs scale of mineral hardness. The softest of all those minerals is something that you've used before in talcum powder. It's so soft that you can put it on a baby's bottom. So the softest mineral is talc. The next mineral is a very common mineral. It is called gypsum. Now I know these words are very new at the moment, but soon you'll get to know and love these minerals well. So I could easily scratch talc with gypsum, but I can't scratch gypsum with talc. The next one is calcite, and the next one is fluorite. Now the fifth one is one you probably never see much in nature. It is called apatite. And the sixth one is the most common mineral in the entire world, and I betcha you have no idea what it is. I'm right. It is called feldspar. Number 7 you've heard of. In fact, I just mentioned it. It's quartz. And number 8 is rather nice because it is a gemstone, topaz. And number 9 has forms in which are also gemstones, but the common form of it is just called corundum. Now, I'm going to make another bet. I bet you know what the hardest mineral in the world is. Oh yes. Diamond. You can use a diamond to scratch anything you want, but you cannot scratch a diamond. Now, what we tend to use to figure out the hardness is our fingernail. I can use my fingernail to scratch anything less than my fingernail, talc or gypsum. I can use glass to scratch anything softer than glass. We'll forget about this, but sometimes you have a knife handy, so a knife could help you figure out feldspar and lower. So what's harder? The glass in a pair of glasses or the rubber in a rubber ball? Well, I think you agree with me that I could take a piece of glass and cut rubber, but I can't take a piece of rubber and cut glass. So the glass is definitely harder. However, what happens when you drop these? The ball bounces. No problem. You drop the glasses, what do you get? A broken pair of glasses. So glass is brittle. It breaks easily. And clearly being brittle is very different from being hard. The hardness refers to the ability of something to resist being scratched. Well, brittleness refers to what happens to it when you subject it to some kind of pressure, such as dropping it. That's why you can cut a diamond. You don't scratch the diamond with something harder than it. You simply hit it in a way that causes it to shatter the way you want it to shatter. That must be a very hard thing to learn. So we've been talking about a mineral's tenacity. The tenacity is a mineral's resistance to being broken or bent or deformed in any way. A mineral could be brittle, like diamonds, or glass. They could be elastic, like the rubber ball or mica's elastic. That is, it bounces back into shape once you've tried to deform it. It could be malleable. Malleable means that you can bend it into whatever shape you want to. Great example of that is gold. Gold is the most malleable mineral, and that's why it's so useful to us. We can bend gold into any shape we want. We can pound it into a foil that's only a few atoms thick. It could be fibrous, like this asbestos. It could be sectile. You could carve it with a knife. Or it could be flexible. That is, you can bend it, but it doesn't snap back into shape. Many minerals will break along distinct flat surfaces called cleavage planes. So the cleavage, the way in which minerals break, will tell you a lot about what kind of mineral you have and its structure. It is the atomic structure that gives a mineral its cleavage. For example, this mineral, you get very evenly spaced atoms, and the weak bonds tend to be the yellow bonds here, and as a result, if it were to break, it would break along those yellow bonds. The result would give you two flat surfaces, and those surfaces are at a 90-degree angle. The result of this breaking gives us cleavage planes. In this galena, or this fluorite, you can see the flash of light over distinctly flat surfaces. These are not man-made surfaces. This is simply the result of the breakage of a mineral. A great example is the cubic cleavage of salt, halite. Now, salt will break into cubes, and if you break the cubes, it will break into smaller cubes. So in fact, if you take a look at the microscopic level, you still see those nice cubic cleavage planes. That would be 3 cleavage planes at right angles. Another mineral with 3 cleavage planes is calcite. However, calcite doesn't break at right angles. As you can see, it's got sort of this rhombohedral thing going on, like a parallelogram. And once again, if you were to break it, you'd get a lot of small parallelograms. Keep breaking it, and the more you break it, the more you get smaller and smaller, tiny little pieces. But each piece will show you the same kind of orientation of this cleavage plane. So it's not just the number of cleavage planes, but also the angle between them that helps you to distinguish this mineral, calcite, from halite, which has cubic cleavage. One of the best way to figure out whether you've got cleavage planes is to smash a rock. Trouble is, you don't always want to smash a mineral, so you have to look at it really carefully. What happens is that if it has a cleavage plane, you'll get a flash of light off of the surface. And sometimes you have to hold a mineral up to the light, move it around before you see those flashes of light. Not everything will be as easy as the examples I gave before. Looking at that, you'll see that not every part of this piece of feldspar has an obvious cleavage plane. However, you get a lot of flashes of light off of it. This is better shown in lab. You'll try this tomorrow. See, flashes of light. Now, some minerals have a cleavage plane, but the minerals are so tiny that you can't see the cleavage plane. One reason that talc is so soft is that it's got one cleavage plane. It breaks really easily, but the crystals are too small to see. That's why when you rub your hand against a piece of talc, little pieces come off with it. You think that the talc feels nice and smooth and soapy, and you end up getting little bits of talc on your fingers. Here's fluorite, one example we have of 4 cleavage planes. You're looking at it from one side and you can see 4 different surfaces. 1, 2, 3, 4. Move it around and you see the same 4 surfaces on the other end. So those 4 surfaces will be parallel. So it'd be the same 4 cleavage planes, not at right angles. If a mineral doesn't have clear cleavage planes, it might also have some kind of fracture that you can identify. For example, this is a piece of obsidian, volcanic glass. It's got great conchoidal fracture. That is, when it breaks along a curved line. Quartz also has conchoidal fracture when it breaks. So when you break it, instead of having a nice smooth surface like it has on this outside, you get a curved surface. Those curved surfaces are called conchoidal fracture.